Are we going for sound, guys? Cool. Nice small class to work with today. We are going to be looking at complex numbers today, people. So, is there any particular ones that you want to work on? Otherwise, I was actually going to work through some excellence questions from 2013. Let me know in the chat, and then we can actually go from there. Just rearrange everything here on this side. Level 3 complex numbers. Hi Ice Bear, welcome Tushar, welcome Ninja Pirate. Got a few folks here. Oh, Brad Eddie, you've got that's a bit stink, but look, you still got TEG to work through, geometric reasoning. You've got a few things to get through, so keep your head up. Is that level 1, Ice Bear? Oh wow, that's crazy, Ice Bear. You're right. Yeah, guys. Today I'm gonna be doing year 13 work. So it depends. I mean, if nobody's here for year 13, then we can always just readjust and redo it. Oh, congratulations, Jaden. That's really awesome to hear. Now it's funny is like after mocks it just goes super quiet. People are like, nah, I'm not gonna do any study in week 10. That's good to hear, Jaden. And Brother D, yeah, Mr. Subramani he's good value. He's very good value. It's mixed, Stanley. I mean, like you get, like I can't really keep track of that, but because I just have a look at the videos and I can see that the level 1 videos tend to be up a lot more. I've got to ask. I mean, is there actually any year 13s here, or is it just level 1s hanging around? Because we could always just change it back to level 1. Yay, Hayden, you're here. All right, Hayden. Since it's complex numbers, is there any particular thing you want to work on? I mean, I don't mind doing either excellence questions, or we could do complex roots. Just yell out what it is that you want to work on, and we can actually work through that. A good one is the rearranging ones. Those ones are good ones. All right, let's just do complex roots then, just because Drew's come up with the answer here. All right, Drew, let's do complex roots. All right. So what I'll do is I will pull up some of my old notes, and then we should be able to go through with that. Give me 1 second. I just need to pick up my old roots. I don't know where I have it. Here we go. Session 13. No. 11. Give me a second, guys. Give me a second. All right. So logs, sometimes it comes, but not that I know of. Okay, so we're gonna kind of go through complex roots at the moment. All right. So what I'll do is I'll give like a bit of a crash course. what we'll do is like we'll do a crash course of complex roots, and then we'll actually do some questions after that. All right. So what I need to do here is just kind of having a look at my notes. Give me 1 second. I always forget which is my zoom button. Got it. Okay. So yeah, Stanley, no, I kind of do it till level 3, and so I get, you know, I guess most of them would be level 1, but then we can, I never really keep track of it. But anyway, let's go through this. All right, now I'm going to start off with really simple, right? Like simple thing is like when we do square root of 9. Right, when we do square root of 9, we actually get 2 answers. The first answer is actually plus 3, and then our second answer is actually minus 3. Because if you think about it, when you do 3 times 3, you're going to get 9, and when you do minus 3 times minus 3, we're going to get positive 9 as well. But when it comes to when it comes to complex roots, now there's a couple of things that we need to kind of understand. All right, so we kind of, I mean, like if you think about 9, how do we put this? 9 is like to the power of half, and this 9 to the power of half is 3. But when you think about complex roots, now like any kind of complex number can be written as z r cis theta. Now that means we could actually go z to the power of n would actually be rn cis n theta. Now this is something that you would have done in very basic kind of De Morris theorem. So in other words, if we then think about like a value, like sometimes they do like this with complex roots, they'll do something like z to the power of n equals I don't know, some number. All right, we don't know what this number is, but it could be like some number. And then what we're trying to figure out is like, okay, so how many different roots are there? So for example, it depends, right? Like I mean, if you have like I'm trying to show you guys with Zn, so I could actually replace this with like Zn is equal to r cis theta. Then I could actually go, well, I want to have z by itself. So what I'm doing is z to the power of n times 1 over n. And then this is all equal to r cis theta. And the whole thing is actually to the power of 1 over n as well. So when you have z as the first, so then it becomes like z to the power of 1 is r cis theta to the power of 1 over n. Now the problem is that, you know, like then we kind of use De Morris theorem again. Now look, this is all just theory at the moment, so don't stress too much about it. So this would become like r to the power of 1 over n, and then cis times theta times 1 over n. So this is pretty much kind of like your first kind of idea behind it, right? Like, so this is quite important. Like this part right here in the yellow box is pretty much important for you. Now there is a couple of ways of doing this. Like there's actually one called, you know, there's a long method of doing this, which is using the formula, and then I have like kind of like a cheap shortcut. So what I'm going to do is I'm going to kind of show you guys both of it. Now I'm not sure if the formula for complex roots is given in the exam, but let me just check. Calculus formula sheet level 3, because I thought they did give it. I could be wrong. Z. No, they don't actually give the complex roots one, but they just give. Let me just show you guys here. Okay, so they do give you De Morris theorem, which is the r cis theta n. But apart from that, I don't think they actually give you the actual formula for complex roots. No, they don't. So this is part of the reason why I actually came up with the shortcut method. And to be honest, the shortcut method is fine. You can use it, and it still kind of works. So the best way to do this is by doing a little example, all right? So think about it like this. Like if I have something to the power of 4, now let's say I'm gonna do this best with an example, guys, because seriously, when I do an example, it just kind of starts making sense. So your question might look like this. So solve z to the power of 4 equals 1 plus 1i. Now this is actually z to the power of 4. That means you're going to actually end up with 4 different answers, or like 4 roots, right? That's the kind of idea behind here. And so what we're then going to do is there's a few steps that you need to do. The first step you need to do is write this complex number in polar form. And then once you write it in polar form, then you apply De Moivre's theorem. And then you could actually use the formula they have for complex roots. Now the formula itself for complex roots, it looks like this, and to be honest, I don't remember it because I don't actually use this, but you guys might have seen this particular formula, which is r to the power of 1 over n cis theta over n plus 2 pi k over n. You might have actually seen this in your books, this formula in the green box. Now you are actually allowed to use that formula. It's still going to come up with the same answers, but you know, I kind of like doing the shortcut method, because with the shortcut method I can do this in about less than 2 to 3 minutes. So I'm going to show you guys a shortcut method first today, and then I will get you guys to do a couple of more extra questions on just shortcuts of this shortcut method for this, and then see how you guys go about it. All right, so the first step we're going to do is we want to write this in a polar form. One of the best things I would recommend you guys to do is actually draw the complex number. So if you look at the complex number in this case, we've got positive 1 and 1, and so this complex number actually looks like this. Now we need to actually work out the modulus and the argument. Now the good thing is we already know what this this distance here is, from here to here, is about 1. I should use a different color. And then the height of this triangle is also 1. So if I break it down separately, I've got a triangle that looks like this, where the base is 1, the height is 1, and because of that I straight away know that this angle here is 45 degrees because it's isosceles triangle. And then we've got to find the hypotenuse. So remember that the hypotenuse is the modulus. So I've got 1 squared plus 1 squared is equal to 2, and then if I write that as h squared is equal to 2, so then h is equal to square root of 2. So I can rewrite z to the power of 4 as square root of 2 cis 45 degrees. That's not a problem, Joel. You're welcome for that. So let me know if there's any questions with what I've done so far. You're welcome, Richie. You're welcome. It's not a problem at all. So let me know if there's any issues with this part so far, that what I've done, the square root of 2 cis 45. Because this is pretty much the first step that you always have to do when it comes to complex roots. You have to convert the complex number into polar form. Yeah, now look, if you want to do it in radians, then you would actually, no worries with radians. I might actually just do it here. So let me just move this. Hang on, give me a second. So if you were to do this in radians, then you would get z to the power of 4 is square root of 2 cis pi over 4. Now I would say to you guys, like with complex roots, it's super easy to work with degrees, and the thing is, like, you don't have to give your answer in radians. You can actually give your answer in degrees, and my recommendation is, if you do it in degrees, it's super fast to actually answer this question. With radians, it still takes a little bit more time, but I would definitely recommend degrees. All right, So Zan, I've actually done a 2018 paper, so you can have a look in my playlist, buddy, for complex numbers, and you will actually find it there. Hey, Rice. All right. So what's the next step? Now here is the next step. All right. The next step is that the next step is trying to work out what the first root is. Now the key thing is this. All right, here we actually have z to the power of 4. Now because we have z to the power of 4, that means you're going to have 4 roots. And if you think about it, each of those roots are split equally, the what do you call it, the distance between them. So if I actually have like something like this is the Cartesian plane here. Let's say this is my first root. Then the difference between the first root and the second root is 90, 90, 90, and 90. So basically, if you have like 4 roots, then each of the roots will be separated by like 90 degrees. And if you have like 3 roots, it would be 120, 120, and 120. But because it's z to the power of 4, each of the roots is going to be like 90 degrees away from each of the other roots. So all you have to do is just figure out the first root. And once you figure out the first root, what you do is you actually add 90 degrees to the argument, and you're pretty much good to go. Now, what I'll do is when I finish this, I'll show you guys in the calculator how it actually works out as well. So I need to figure out what my first root is. To figure out my first root, I'm going to go z to the power of 1. Now, I need to get rid of that 4. So I am going to multiply it with a quarter, which equals to square root of 2 cis 45 degrees to the power of a quarter. So my first root is going to be z1 equals square root of 2 to the power of a quarter cis 45 degrees, and we're going to go times a quarter here. So that's pretty much following that formula from the yellow box. And basically, when I do this, I'm going to get my first root, which is square root of 2 to the power of a quarter. If you really want, you can write 2 to the power of 8, or you could just leave it like that. It doesn't really matter with these things. But the 45 times a quarter of 45, that one is really important. That one we want to write it as 11.25 degrees. Now this is my first root. So if I look at my second root, all I've got to do is the modulus is still going to be the same, and then I'm going to actually add 90 degrees, because remember I told you guys that each of those roots are going to be 90 degrees apart from each other. So this will become 90 plus 11.25, which is 101.25. Then the third root will become square root of 2 to the power of a quarter cis 101.25 plus 90, which is going to give me 191.25. And then finally, the fourth root is going to be square root of 2 to the power of a quarter cis 191.25 plus another 90 degrees. So in this case, it is going to be 200 and what do we got? Sorry, I'm just looking at something else here. I'm just getting distracted. Yeah, 281.25. So basically, I've actually got my 4 answers. So that's my first 4 roots. So first, second root, third root, and fourth root. And that's pretty much it for complex roots. Now what I'm going to do is I'm going to show you guys. So let's say I take the calculator here, and what I'm going to do is I'm going to do the first one, which is square root of 2. So square root of 2 to the power of quarter, which is 0.25. Now with cis, right? With cis, the way you have to actually enter cis is you've got to split it up as cos and sine. So I've got to go times cos of 11.25. Actually, I just want to make sure that the calculator is set up to degrees first. Cos of 11.25. What shall I do? I'll actually put this in a bracket actually. So give me a second. Cos of 11.25 plus I sine, so it'll become I sine of 11.25. Hopefully this works. Okay, so this is what one of the answers is. Now if I put this to the power of 4, I should get 1 plus 1i, and I really hope it works. There we go. So as you guys can see, that is one of my roots. So that first 11.25 ends up being one of the roots. All right. Now, if I try the same thing with 101.25, so I'm going to go back. Where is it? 101.25. Okay, there we go. And I'm going to change the 11.25 to 101.25. So this is the new complex number, and if I raise that to the power of 4, I get 1 plus I again. So what I'm trying to show you guys is that there's actually 4 answers for Z4, and each one of those answers, if I raise it to the power of 4, I'm always going to get that 1 plus 1i. So what I'm going to do is I will leave this up here for now, and I might put some line numbers. So if there's any kind of line that you guys have a question with, feel free to ask. Otherwise, what I'll do is after that, I'll actually put up another question for you guys to try and do it by yourselves. I'll actually leave the working on the side there so you can kind of see what we're trying to do. Marco, glad to help you. No worries. Oh, no worries, Zed. That's good to hear. Remind me tomorrow. Algebraic procedures and solving problems. Haste. I think you need to be a bit more specific. Welcome aboard, Nick. Hey, Croza. No, Hayden. This is generally a merit question. It's like it's not a. This complex roots is hardly an excellence question. It always ends up being a merit question. The one year that I saw it as a excellence question was almost 10 years ago. Oh, 828. That's gotta suck, Rosa. Chloe, I'm not sure what you mean by schedules for NCA level 1. I mean, like, I've done all the working out. But anyway, look, while these guys are asking me questions, I'm going to put up another question for you guys to try and do by yourself. What I'd like you to do is, I'll actually put this question up here. Z3 equals, what should we do? Hang on, I'm just looking at the question at the moment. Yeah, let's do this one. No, not Z3, let's do Z4. Actually, no, sorry. Let me try this one. Sorry, guys. Let's try 1 plus 5i, and we're going to make the z cubed. Sorry about that. I'm just trying to kind of look at a couple of different variations of questions for you guys so that you can actually get a good chance of answering this. So try that one. So we're going to try z cubed equals 1 plus 5i. Word for word, that's the standard is called word for word. Algebraic procedures in solving. Oh yeah, that is the level 1 MCAT haste. I thought the MCAT's already over. Good to hear, Marco. Good to hear. Oh, thanks, Nish. That was good fun, but it's back to the grind now. Yeah, algebraic procedures is generally, yeah, you're right. It is Rihanna is correct. It is the MCAT. Yeah, that's okay, Dhruv. It doesn't matter if the argument is 78.69, and I think that's why you kind of use you just add 120 degrees after you divide it. So I purposely didn't give you guys nice numbers because I wanted you guys to kind of work through different versions. Now, Haste, you've got 3 more. You've got tables, equations, you've got geometric reasoning, and you've got chance and data coming up in November. I don't know which one your schools will be doing. Nish, it's a great experience. If you can do it, why not? You got nothing to lose. Crozer, that's I've seen that question before, and I know what how to do those ones as well. So there's a trick to it, usually with the letters. But look, let's actually do this one here. The z cubed equals 1 plus 5i. So step 1, we are going to actually figure out what's happening with this in terms of polar form, right? So we've got to do that first. So I'm going to draw this little graph here. So 1 is in the real axis, 5 is in the imaginary. So we've got a complex number that's looking like this. So we need to figure out what the hypotenuse is, and we also need to figure out what the argument is. So I've got a little triangle that looks like this, where this is 1, this is 5, and I've got to figure out what the angle is. Now, with the h squared is equal to 5 squared plus 1 squared, h squared is equal to 26, and then h is equal to the square root of 26. So my z3 equals square root of 26 cis, and I've got to figure out the angle, and for the angle I could do tan theta would work, but like I'm just gonna check it, all right, because sometimes the angles can play up, and tan is a very tricky one to use. That's why I prefer using sine, but like in this case I think it might be fine. If I go inverse of tan and 5, I get 78.69 degrees. So the argument is let's just say 78.7 degrees. So I'm going to put this down here. This is what z cubed is as a polar in polar form. So when I do z to the power of 1, so z is equal to this entire thing, square root of 26 cis, 78.7 to the power of 1/3. So my first root is going to be square root of 26 to the power of third, cis 78.7 times 1/3. So z1 is equal to square root of 26 1/3 cis, now 78.7 times 3, I get 26.2 degrees. Now remember, we're actually doing z cubed, so if it's z cubed, then you're going to end up with 3 roots. I don't think that's right, but maybe something like this. So each of the roots is going to be separated by 120 degrees. So I'm going to add 120 degrees, and I'm going to get my z2. So z2 is equal to square root of 26 to the power of third, cis 120 plus 26.2 is 146.2 degrees. And then of course for the third root I've got to add another 120 degrees, which means z3 is square root of 26 to the power of third, cis 266.2 degrees. Now you might be wondering, okay, what happens if I just keep going? What if I add like another 120 degrees? Now here's the thing, all right? If you do add another 120 degrees, you're gonna end up with Z4. Now Z4 is square root of 26 to the power of third, cis 386.2 degrees. But if you notice, this Z1 and the Z4 is actually exactly the same answer, because what it is that you've got 26.2, but because you're going 386.2, you've actually gone back a full circle. You've actually gone 360 degrees, and then you're adding that 26.2, and that's why it's coming up as 386.2. So, you know, it just means that once you finish that cycle, because it just keeps going, and you're going to keep getting like multiple roots. But we kind of stop at those those roots between 0 to 360 degrees. All right, so that was one of the more, like, not complex questions, but it's just like kind of made it a bit more trickier for you guys to try and do it. But next one, what I might do is I might just put a different question and then ask you guys to find the roots. And I'm gonna put down, this time I'm actually gonna put down some what do you call it? I'm gonna put down some letters just because it's fun. By the way, is there any questions on this one? I'll put up some line numbers again. 1, 2, 3, 4, 5, 6, 7, 8, 9. All of this is 10. So let me know if you've got any questions from that so far. And if you don't, then I can actually give you guys the next question. But what I'll do is I'll put it on the side here so that, you know, if people want to work on the next question, they can. So the next question we're going to be looking at is this one here. And that's all I'm going to give you guys there. Oh, actually, no, wait, hang on. Let me just put this. Yeah, that's better. So what I might do is I might give you guys like, what is the time? 8:34. So I'll give you guys till 8:36, and then I'll go through the answer at 8:36. No worries, Jacob. I think I just saw your comment pop up as well. Where did you comment? I don't know where you wrote it. Just convert it, Dhruv, to polar form, and you'll be pretty much good to go. Oh, thanks, Zoe. It's been a bit of a crazy week, I have to say, and but it's like I said to the guys before, it's back to the grind at the moment. But it was pretty cool. Okay, so we're gonna try this question here, because I know that Dhruv, you kind of went, what are we doing here? So as I said to you guys before, anytime you kind of see these types of questions, the first thing you really want to do is to convert it to polar form, right? So what we're going to do to convert it to polar form is we're going to need to draw a little diagram, all right, just to see where this particular complex number is. Now right now it doesn't have any real value at all. All it has is just it's 16k to the power of 8, and it's imaginary on the imaginary axis. So we've got this value here, which is 16k to the power of 8, and that's pretty much it. The complex number is like that. So if you look at the distance or the modulus of this complex number, it is going to be 16k8, and the argument is going to be from here to here, which happens to be 90 degrees. That is pretty much your first step there. I'm going to pause there just to see if there's anybody that have any questions there before I carry on, because I think once you get to this part, you guys will actually know what to do. So if you want, you can have another minute to try and work it out, but if you do have any questions as to how I got there, feel free to ask on the chat, and otherwise I'll go through the answers in about half a minute. Zan, I'm not sure what you mean by are the angles 90, 180, 270 and 0. First order. It's my got a few of those Star Wars t-shirts. Well, Drew, if you think about it, modulus is actually the length of the complex number, right? Because if you think about it, if it's in a triangle, like let's say if it's in a triangle, if that's the complex number, what you're trying to do is you're actually trying to find the modulus of this, which is literally the length of that line, of that complex number. But when you have when it's like straight or down or left on right, if you think about the length of this, which is already 16k to the power of 8, that becomes its modulus, because that is the length of that complex number. Now you could do the square root of a squared plus b squared, Drew, and if you think about it, a squared in this case, a is going to be 0, b is equal to 16k to the power of 8. So if you go h squared is equal to 0 squared plus 16k8 squared, you're going to get h squared is equal to 16k8 squared, and then h is just equal to 16k8. So you can still do the a plus b thing, but you're just wasting time. You don't really need to do that. Now once you guys get your Z4, you could actually get what Z is. So then we can actually write that Z is equal to 16k to the power of 8 cis 90 degrees to the power of a quarter. So Z1 is going to be 16k to the power of 8 to the power of a quarter cis 90 times a quarter. So we're going to get Z1 is equal to, now 16 to the power of quarter is 2, and then 8 times quarter is just 2 again, so we're going to get 2k squared cis 45 times 90 divided by 4 is 22.5 degrees. Now once again we've got z to the power of 4, and because we have z to the power of 4, we're going to get 4 roots, so 360 divided by 4 equals to 90. So we're just going to add 90 to each one of the solutions. So plus 90 is going to give us our second solution, which is 2k2 cis 112.5 degrees, plus 90 to get the third one, which is Z3 is equal to 2k squared cis 202.5, plus 90 to get the last root, which happens to be Z4, 2k2 cis 292.5 degrees. And that's pretty much it for this question. So Jacob, we're doing De Moivre's theorem there. Right at the beginning, you've got to do De Moivre's theorem. So it's like you're actually taking, you know how you go from Z4 to 1, you multiply by a quarter. So I'm doing right hand side by a quarter. By the way, that was pretty close to a merit question from like a few years back. I just pulled up and changed some of the numbers. Minus K6I. Yeah, we'll do another one, guys, because like this question always comes in complex numbers, and it's one of those questions that's like worth knowing because it's actually one of the easiest merit questions, I feel anyway, in the complex numbers paper. So if there are no other questions with that, I'm gonna give you guys your next question, but this time yeah, I'll give you quite an easy one to kind of start off with. But what if I do this? Yeah, I'm gonna try and do this. Give me a second. Let's try this question here. So solve yep, I'm gonna give you that as my next question. So for this one, what I'm gonna do is I'm gonna give you guys about 3 minutes maybe. What is it, 8:43? So we'll go through the answer at 8:46. Hey Jack CV, welcome aboard. I'm gonna see if this actually works or not. How do you, let's, oh wow, okay. So I can't actually change the quality. Auto is 480. Okay, it's not too bad. Yes, oh Jack, you don't need to put that dollar, man, come on, like, seriously. Keep that, look after yourself. TEG's tomorrow, Matt. What? That's crazy. Wonder if James, are you actually in the live chat, or I can't see a James here. All right, guys. So let's go through this question. I mean, has anybody got an answer yet? You're gonna get frustrated when you see this question because you're gonna be like, "Ah, why didn't I think about it like that?" Very nice, Jack CV. That's this. Congratulations. All right, I'll give you guys another minute then. Nishat, I actually did a kinematics one last week. Have a look, right? Because last week I did kinematics for level 2. Okay, so let's go through this question here. So the first thing I'm going to do is I'm going to sketch where this thing is. Now I know that this right here is 1p, and then this here is going to be square root of 3p. So my complex number is going to look somewhat like this. So if I create a triangle for this, then what I'm going to get is I'm going to get p here, and I'm going to get square root of 3 p there. All right, so now here's a really interesting thing, guys. Oh, Jacob, you didn't need to, but thank you so much. What I'm going to do is I'm going to show you guys this right here. This is quite useful, this. And sometimes it happens, right? Like they use these weird numbers. Like if I go back to this question actually has a 1 and a square root of 3. Now it's really important that you recognize these numbers, like 1 square root of 3, because why? When you go into the formula sheet, there is something called a special triangle, and that's right here. All right, so what I'm going to do is I'm going to copy this special triangle and see if I can dump it in the current paper that we're working on. 2023 complex numbers. Where is it? Okay, clearly I need to be doing this. Where is it? Sorry, just give me a second. I'm trying to figure out. Oh yeah, here we go. Where did that triangle go? Thing is, the copy paste on my OneNote to PC to OneNote takes a bit of time. Hopefully this triangle comes up very soon, and then I can actually show you guys how it actually works. It's kind of there, but all right, let's go back to the main recording. So come on, triangle, move. There it is. So I hope you guys can see this link here right now. This is P, this is P, which means this is also going to be P. So what we can actually do straight away is Z cubed is equal to 2P. Right, the modulus is going to be 2P, and the angle, so cis, because if you look at it, I mean, this is 1 and this is square root of 3. So if you actually do that, which we don't need to because it's already given in the special triangle, that's pi over 3, which is actually 60 degrees. So your answer should have been, like when you write it in polar form, it should be 2p cis 60 degrees. All right, now I know that like sometimes you kind of see letters and you kind of get freaked out about it, but the reality is that the reason they put those letters, particularly like when they have like 2 letters like this, is, you know, you've got to look at it as a ratio and not as like the letters, because some people go, well, how am I supposed to put like tan of inverse tan of square root of 3p over 1p? Well, you only put the square root of 3 and the 1. You don't really worry about the p because they cancel out each other anyway. Because think about it, like if I do tan of this, I'm going to get tan of inverse tan of square root of 3p divided by 1p, and basically those 2 p's, they cancel out each other. So what you're really doing is inverse tan of square root of 3. But because we've already got the special triangle, so we can just pick it up straight away. So we're going to get 2p cis 60, which means z is going to be 2p cis 60 to the power of a third, and then z1 is going to equal 2p to the power of third cis 60 times 1/3. So z1 is equal to 2p to the power of third cis 20 degrees. And because you've actually got 3 roots, you do 360 divided by 3 roots. That's going to give you, each root is going to be like 120 more than the previous one. So we're going to add 120. That's going to give our second root, which is 2p third cis 140. Then we add another 120, which gives us our third root, which is 2p third cis 260 degrees. So that is pretty much it for this question. Like, I mean, that's the whole point of like using the shortcuts in these types of questions, because you can just kind of finish it in like, you know, a couple of minutes flat, and you're done straight away. Any questions on these ones, guys? Quiet time today. All right, guys, look, that is, I'm gonna call it today with that one, because like my throat's about to die, and that's pretty much most of the questions in complex roots that we can actually cover. There's really nothing else, unless they kind of ask you some quadratic within the complex number question, which was an excellence back in 2013. So I don't think you're gonna see any kind of like crazy complex roots question like that. But that's pretty much it for today. I'm gonna kind of call it a bit early today, and then go chill out at not really chill out, it's more like I've got to do some work later on for other things at the moment. But that's pretty much us today, folks. So have a good night, and I'll hang around for a couple of minutes just as I kind of pack up and things like that. But thank you for joining me today, and I appreciate your time. No worries, guys. You're welcome. Goose night is it indeed. Hey, do we want to continue this during the holidays? I keep meaning to ask you guys, but I know some people wanted to do like a big, massive differentiation session or an integration session. Would be cool to kind of get some feedback. Please don't, Nishat. Please don't. Okay, so that's kind of sold. So what I'll do is I'll work out some time, and I'll kind of upload a picture at I'll upload some pictures, not pictures, what do you call it, timetable schedules, to kind of like work through it. All right. But yeah, no, it's good fun. And we'll try and just work through the next month, because I didn't realize this, but the exams are like super close with each other. Like I think it's like what do you call it, it's within a week there's calculus level 2 and level 1. So I think by November 8th or 14th, when is it, November 8th, I'm going to be done with this live streams. NCA timetable 2023. So calculus is, when is calculus? Level 2 maths is first on 8th of November. 9th of November is level 1 maths. And then Monday 13th is calculus. So I'm done on Monday 13th of November, which is pretty insane. Like normally I tend to go, no, last year was pretty fast as well. Dhruv, we are, my son and I have been talking about it. Like we've actually talking about creating this massive world where we can actually invite people to come and join and build. We just haven't decided what we're going to build. So once we do that, we'll put it out there. So maybe you can come in and help us build something. How do I know when you're going to upload level 3 calc videos? Viggy, I think the best way to do that is just kind of subscribe, I guess. That's the best way, because when you subscribe, you get notifications that come through. Other than that, check out the, like, normally on Instagram and YouTube socials, I put up my live stream tutorials, and I think that's the best other time that you can think about. But we'll figure out the two triangle quadratic. Martin, I'm not sure I'm following you. Did I miss something? Did I miss a comment from you? No, I see 3, thank you. Not sure where your question was, Martin. Quadratic space. All right, guys, look, that's it for today. Have a good night. I think I'll see you guys next week, and we'll kind of work through that level 3, rest of the level 3 tutorials. All right, but yeah, no, have a good night, and I will catch you guys if I don't see you before, which I won't. Enjoy the good start of holidays for you guys. All right, good night.